Welcome my students as well as the viewers. Today I am going to explain this Karl-Pearson correlation coefficient, or it is known by the name product moment correlation coefficient. In the previous video I had discussed this one and about the theoretical aspect of the correlation. I had in few minutes I had explained what correlation is, what are the various kinds of the correlation. And since right now we are interested in simple correlation, that is the correlation between two variables x and y. Now, when we try to investigate the correlation between two variables x and y, first of all we draw the scatter diagram relating to the given data what we do have. When we draw the scatter diagram, we get 5 kinds of diagrams showing different pattern of a scatter of the points in 2D diagram. And by observing the nature of the scatter of the points, we could conclude that this correlation is positive, or it is a perfectly positive, or negative, or perfectly negative, and sometimes there is an idiotic correlation where those two variables are not related in a further way too. So there we get the zero correlation, or the zero. So from the scatter diagram, we just have an idea of existing correlation between x and y. It does not give us the exact measurement. Of course, it gives us an idea that what kind of correlation exists, and in what limit it is likely to fall. If it is positive, then R lies between 0 and 1. If it is perfectly positive, then R must be equal to +1. If it is negative, then R is in the limit of greater than -1 and less than 0. This is negative correlation. If it is perfectly negative, R is -1 and R is 0. So this scatter diagram only gives us a limit within which the correlation is likely to fall. It does not give us the exact measurement of the correlation. So for knowing exact correlation numerically, we look for the different methods, and among those different methods for this correlation, the most important or the most famous measure is the Karl-Pearson correlation coefficient, or it is known by the name product moment correlation coefficient, which we are going to investigate that in what different ways it could be expressed, and that could be used according as per the given data for our own comfort and luxury. So we are going to investigate this Karl-Pearson correlation coefficient. Originally, this Karl-Pearson correlation coefficient is defined as the ratio of covariance xy divided by standard deviation of x and standard deviation of y. This is the original formulation of Karl-Pearson, because when the gentleman Karl-Pearson was constructing the formula, his main purpose was to know the covariability between two variables, and for knowing covariability, covariance would have been enough. But since covariance has its own units of measurement of x and y, so in that case any statistical measure must be free from unit of measurement, and only covariance would have its own units of measurement x and y. So just to remove this unit of measurement of x and y, Karl-Pearson was forced to take the standard deviation of both variables in the denominator. This is what the real idea behind this formula is, because covariance is enough to express the covariability between x and y from their own means, from their own averages. It is apparent in the formula. And if covariance xy would have been Rxy, then this formula must have been with their own units of measurement of x and y, and just to remove those two units, this covariance was divided by the standard deviations of both variables sigma x and sigma y. Now, we do have the formula for covariance xy, sigma x and sigma y. The very covariance between x and y is defined as the arithmetic mean of the sum of deviations of x and y from their own mean. Once again, covariance xy is defined as the arithmetic mean of sum of product of deviations from from own means. That is the means of x and y. That is x bar and y bar. This is covariance, and this is the standard deviation of x. This is the standard deviation of y, and standard deviation is defined as the positive square root, whatever I am spelling out, and exactly it has been written. So SD is positive square root of the arithmetic mean of sum of squares of deviations from mean. Exactly, this is the standard deviation of x and y. Now here, this 1 by n in a square in root, and here it is 1 by n, so definitely it will cancel these two. So what we do have, summation x minus x bar into y minus y bar divided by under root summation x minus x bar square and summation y minus y bar square. Quite apparent from this original formula. If in next stage, this is original x and this is the mean of this x, so it has been written in the capital letter from now on in correlation, particularly in these two classes. There is a difference between this capital X and small x. Here small x is defined. If we define x minus x bar as a small x and y minus y bar as a small y, we are going in deviation form. X has been deviated from own mean and y has been deviated from its own mean. So this original formula is getting converted into a deviation form. So this could be written as summation xy divided by under root summation x square and summation y square. Yes. Taking these two in one root, nothing different. This form of Karl Pearson is known as the deviation form. This is known as, I call deviation form of Karl Pearson. Now come on. If we don't go in this way, and if we expand this thing, then we are going to get n summation xy minus summation x summation y and divided by under root n summation x square minus summation x whole square and n summation y square minus summation y square. Of course, there is some algebraic work from when you come from here to this point. In between, there is some algebraic work that this is what I am just bypassing in the class. This form of Karl Pearson, in henceforth, this is known as non-deviation form. Non-deviation form. So it must be clear that mathematically there is no difference between this deviation and non-deviation form. Both are the identical statements. Both have been derived from this one. Covariance xy divided by standard deviation of x and standard deviation of y. But for our own convenience, these two forms of Karl Pearson would be used at two different places for our own comfort. That must be made clear right here. This non-deviation form must be used when both x bar and y bar are, or any one of them is fats.